Hello everyone, welcome back to this course on reinforced concrete design. We are in the 6th week of this course and this is our first lecture. In this week, we are going to cover foundation design. Now, we also call it substructure. And there are different types of substructure or footing. For example, isolated footing, then combined footing, then strap footing, then mat footing. We also call it raft, and then pile foundation. Now, let us first see the schematic diagram of a isolated footing. So for that, we have a small pad-like structure that transfers the load from the column to soil underneath. So it is buried inside the soil and hence it is called substructure because it is below the ground level. Okay. So this is the ground level and the load coming from the column is actually transferred to the soil below. Now, depending upon the quality of the soil, that means how much resistance it can generate, we have different types of foundations. As you can see here, it is an isolated footing which is actually placed below each and every column. Sometimes we need to combine them. So two columns we need to combine and then we get a combined footing. Now from isolated footing to combined footing, what is the advantage? Because we transfer the load over a bigger area and therefore the pressure below the foundation will be less. Now from combined footing, strap footing means along a line if we have a number of columns and for that we provide a beam-like structure below and then that transfer the load from the columns to the soil strata, so we get strap footing. Likewise, for the entire set of columns for superstructure, if we have a common foundation, we call it a mat or raft foundation. Now, these options, what you can see on your screen, they can be divided into two major groups. The one marked above this dotted line, they are called shallow foundation. While the pile foundation, which goes to the deeper strata, is called a deep foundation. Now, how do you decide which type of foundation we are going to use for a particular site? It all depends upon the bearing capacity of soil. Now, how do we come to know the bearing capacity of a soil? That we'll see in a minute. But before that, let us go back to the isolated footing whose schematic diagram you can see on your screen. Now, depending upon the type of soil we have, just below this pad, we have different types of pressure distribution. So, one of them is, for example, is something like this, which is having maximum at the middle this type of distribution we encounter in case of cohesion less soil. So the natural question comes in our mind, in case of cohesive soil, what should be the distribution? It is just the opposite. So for cohesive soil, we have maximum at the ends and minimum at the center. But when we design the foundation, we'll always go for a uniform distribution of pressure below the foundation. Okay. So in all our analysis, we'll consider a uniform distribution, as you can see here. So this is uniform. We have already seen for cohesion-less soil, and this is for cohesive soil. Now the question to be answered is how to quantify the safe bearing capacity of the soil. So SBC. So SBC is based on the ultimate capacity of the soil that offers. Sometimes we actually quantify this as the allowable bearing pressure based on the tolerable settlement. So for a particular site, the moment we apply load using this column foundation arrangement, obviously there will be some kind of settlement because the soil below is an elastic medium, right? So the moment we apply some pressure, there will be some kind of settlement, and that settlement also will have different components that we'll see in a minute. Sometimes the settlement continues over a longer period, and we also have a long-term settlement of a particular site depending upon the type of soil we encounter. But when we design a structure, obviously we expect the structure not to settle over a prolonged period. Of course, there will be some settlement at the initial stage, and we design the foundation in such a way that this allowable settlement is actually taken care of within the design process. Now, this SBC for a particular site, we can quantify in two different ways. The first one is the plate load test. The second option is Terzaghi's analysis. Either of the two options will give us the safe bearing capacity of a particular site. So the first one is experimental. And second one is analytical. Now, this is not a course on soil mechanics, so we will not go into the details of this. In our design, we need just the value of safe bearing capacity of soil at a particular site, and with that only we can move forward with our design process. Now, before we continue, let us see the bearing capacity, safe bearing capacity at a particular site, which is Q naught is equal to 1 by F within bracket C NC plus gamma D NQ minus 1 times RW1 plus 0.5 gamma B N gamma RW2 plus gamma D. This is for strip footing. I'll explain all these parameters in a minute. For square footing, it is 1 by F 1.3 CNC plus gamma D NQ minus 1 times RW1 plus 0.4 gamma B in gamma RW2 plus gamma D. And for circular foundation, the only change is in the second coefficient. So 1.3 C and C plus gamma D in Q minus 1 RW1 plus, instead of 0.4, here it is 0.3 gamma B in gamma RW2 plus gamma D. So the first one is for strip, second one is for square footing, third one is for circular footing. And as I said, we will not go into the derivations of this expression because our aim is to design the foundation and not the derivation of this expressions. But of course, we should know the details and how they actually are important in the design of foundation. So let me just quickly explain the variables involved in this equations and different other parameters, and then we will see how we can use this in the design of foundations. So this width of the foundation is B, the depth of the foundation is D, then we have F, which is factor of safety. Normally, we keep factor of safety 2 to 3 for foundation design. Just note this, we have a very high factor of safety when we design foundations. Then we have NC, NQ, N gamma. These are called bearing capacity factors. So bearing capacity factors for general shear failure. Now for local shear failure, again, they are replaced by primes. And again, as I said, this is not a soil mechanics course, so we will not go into the details of that. Our main objective is the quantified value of this SBC only. Now, RW1 and RW2 are called water reduction factor because below the foundation water table, which you can see here, so this water table can actually fluctuate, and this water table also dictates the bearing capacity, and for that we have this RW1 and RW2. So RW1 is equal to 0.5 into 1 plus ZW1 by D. So this is ZW1. Similarly, RW2 is equal to 0.5 into 1 plus ZW2 by B. So ZW2 is somewhere here. So depending upon the location of the water table, we have these two reduction factors. Now, we can also find out the allowable bearing capacity based on maximum allowable settlement. So the expression for that is 33.3 N minus 3 into B plus 0.3 divided by twice B whole square Rw1 times Rd. Normally we have a allowable settlement of 25 millimeter. So that is the allowable settlement, and for that we find out the soil pressure corresponding to the settlement, which is in kilonewton per meter square. So what is this N? This is the SPT value with appropriate correction, obviously. This B is the width of the foundation. So we have Rw1 as explained earlier, and then Rd, which is called depth factor. And this is equal to 1 plus 0.2D divided by B, and should not be more than 1.2. Now, when we talk about safe bearing capacity of a particular site, so we actually consider minimum of these two. So we have QP and Q0. So minimum of these two is what we consider the safe bearing capacity of a particular site. Now, total settlement at a particular site is what we call S. It has three components: SI plus SC plus SS. What are they? This is the immediate settlement. So as soon as we apply load on the soil, because it is an elastic medium, it is bound to experience some kind of immediate settlement. Then, because of the consolidation of the soil, we have this SC. So this is for consolidation. And then finally, the last component is the secondary consolidation. Of the soil. All three combined together offers us the total settlement that we consider. And just remember, the maximum allowable settlement for a particular site is 25 millimeter. So that will cover all of them. And if we need to quantify the safe bearing capacity based on that, so we have to actually consider the immediate settlement. Then from the soil parameters, we have to quantify the consolidation settlement, which will again have a secondary long-term component. So all three together will give us the idea of total settlement that the site is going to experience. Now, immediate settlement SI is quantified by this expression. So SI is the immediate settlement in this expression. Q is the contact pressure. B is the width of the foundation. Young's modulus is ES. And then IW, this is called influence factor. Influence factor is, it has different values. For example, 0.88 for rigid circular footing, then 0.82 for square footing, then for rectangular footing, depending upon the size, it varies. So this is the way to quantify immediate settlement. And as I said, we are not going into the details of these expressions because that is not our main objective in this course. But just to know that these are the different ways we can actually quantify the settlement, and ultimately that will reflect the safe bearing capacity of the soil. Now, once we quantify SBC, our design process starts. So this is our starting point. Now, next is our foundation design. obviously as per IS 456, because that is the parent code we are referring to. Now, just imagine we have a foundation. Let us just copy this. So we have the load coming from the column, and then for the timing, the question we want to first answer is, what will be the extent of this pad below this foundation? How big we can actually provide this pad? And if we provide a larger pad, will it be effective? So let us see how we can quantify that. Now, the area is actually limited by the compression that we are going to develop below this foundation. And for that, if we just draw a line, an angle here, as you can see, the load from this, it may be a wall, it may be a column, it may be a wall or column. Just below it, it will be distributed over a wider area. And this alpha, the angle that is important, we'll see what are the provisions given by Indian Standard Code in a minute. But two things for sure, that the load coming from the superstructure is distributed over a wider area. That is the first point to be noted. And then there is a minimum thickness, because if you have a very skinny foundation, then what will happen? This wall or column can actually punch through that foundation and it can break with its own weight. So the thickness of RCC or plain concrete footing have a minimum requirement. So it is 150. So first point to be noted, thickness. It is 150 millimeter for foundation on soil or say shallow foundation. And 300 millimeter if we have a pile. So this is above pile. We have a pile cap. And for that, we have 300 millimeters. So if you have, say, a pile here transferring the load below the foundation, then this thickness will be 300 millimeter, or otherwise, if you have an isolated footing, which we'll consider first, for that 150 millimeter is sufficient. That is the minimum. Of course, if the design requires more depth, we have to provide that. So this is the requirement for minimum thickness. So let us write minimum thickness. Now code says tan alpha should not be less than 0.9 square root of 100 Q0 by FCK plus 1. Q0 is the shape bearing capacity of the soil, SBC. FCK is the concrete property. So, for example, if you use say M20 concrete, it is 20 Newton per millimeter square. So, the relation here, as you can see, tan alpha should not be less than this value. So, we have to maintain that angle. Okay. So, we cannot have a larger foundation pad, then it will not be effective. Also, we cannot have a very, small pad just below the foundation or the column or wall. Okay, then also we will not get sufficient supportive reaction below the foundation. So we have to maintain the minimum size, and that size will come from this guidelines. Now when we design this foundation, for that we have to consider the pressure developed below the foundation. So let us first see the pressure developed, and as I have already explained, we consider uniform pressure distribution below the foundation. That means you can see foundation, we can consider it as an inverted beam which is supported at the center. On the either side, it acts as a cantilever which is supporting this pressure, say P naught. Now, the moment we apply this pressure, this foundation acts like a cantilever beam, and you know the critical section for the cantilever beam, it is supporting a column. Then obviously this face of the column is the critical section where we will have the maximum amount of bending moment developed. So we have to design this foundation as a beam with the bending moment at this critical section. Now, if we have a wall, let me use a different color. If we have a wall, say this is a wall, then this wall sits over this foundation. So we have, this is the center line of the wall. So in that case, the face of the wall is not the critical location for the bending moment. It is just in between the center line. So this is the center line of wall. And from the center line to the face of the wall is the region where we will have the critical section in between. So this is the critical section for wall design. While the face of the column, this one is the critical section for column. Now, when you will design a column as a steel column, so if this is a steel column, then the steel column is not directly supported over a RC foundation, then we have a foundation pad. So let me just show you that first. So we have a foundation pad, then on top of foundation pad we have another base plate. Over this base plate we have the steel column supported. So if this is the arrangement, then instead of taking the face of the column which is here, we consider halfway between the face of the column and the edge of the gusseted base. So this is the base. So this is base plate. Edge of the base plate is here. So at the middle of these two, we consider the section critical. So this is the critical section. For steel column. And we know the uniform pressure acting below this foundation. So we can find out the bending moment at this critical section from the cantilever analogy, and then we can design that cross section. So you can see how the critical section varies for a RCC column foundation arrangement, then from that to a wall and a pad below it, and then finally a steel column supported by this base plate over a foundation. Nevertheless, all three will actually go for this bending moment at the critical section and design this as a beam. Okay, so as a beam we will design. So the first part is answered. We can design this isolated footing as a beam. What about shear force and bond? Now, when we have a foundation, let us again copy the previous one. Let us focus on RC columns supported on RC foundations. And not a steel column, because this is not a steel design course. So for this type of column, if we design the foundation against shear force, there are two options, two situations will arise. The first one is what we call the one-way shear. And for that, let us identify first the critical location. Now, as I already explained, below this foundation, the load will be distributed over an area, and for the shear force, load distribution as a 45-degree angle is important. So if the depth of the foundation, say D, then this section is actually critical for one-way shear. So critical for one-way shear. That means, again, below this foundation, we know what is the pressure developed, and we can quantify the amount of pressure developed on the left-hand side of this critical section, and for that we can find out what is the shear force acting at this section. So how far is this section from the face of the column? We can easily conclude that this is D, because we consider 45-degree dispersion of load from column to the foundation. Now, on top of that, when we have a column, which for the time being we can consider as a square column, and footing is also square, so we have an arrangement like this. So we have the column sitting at the center, and because this foundation acts like a plate supporting a column which is applying a load P at the center, there is a tendency that this square column can actually punch through this plate, and that will distribute the shear force for this punching over a area which is marked here. This is called two-way shear. So two-way shear action will have a wider area, and let me mark, if this is the size of the column, then it will extend on either side as D by 2. So on either side we'll have D by 2 and D by 2. So the total width in that case will be B plus D, right? So for two-way shear, so this is two-way shear, we have to consider this critical section. And we can quantify the shear stress developed, and we can design accordingly. We'll see those design guidelines in a minute. But let us first identify the critical section. For foundation design, the point to be noted when we design it against shear force is that we have to design for one-way shear, where we consider cantilever action, and we consider a section at a distance D from the face of the column and find out the shear stress developed there, and we check the design against shear. Additionally, we have to also check against punching shear, and for that you can see the critical section on your screen, right? Now, for this punching shear, what is the design procedure? Let me quickly go through, because design against Bending is straightforward. We will use the bending formula that we have already covered for beam design. One-way shear, again it is very simple. If you recall, tau v should be less than equal to k times tau c. And then the two-way shear, which is new here. So let us see the design procedures for punching shear. So design against punching shear or two-way shear. So here we have tau v, it should be less than equal to ks times tau c. Now how do we calculate tau v? Tau v is equal to P ultimate, that is the ultimate load coming from the column. So if this is P, P ultimate is equal to 1.5 P. Of course, different load combination will have different factors, but that is a separate analysis. If you have P, that is the unfactored load coming to the column, that we multiply with the appropriate load factor, we get Pu. Now divided by 2 times, we have A plus D plus B plus D, or let us mark it B times D. I'll explain all this in a minute. For that, let us just mark it in a different way. So we earlier considered a square pad. So this expression is general for a rectangular pad, where square is a special case. So if we just consider this pad to be a rectangular one, so say this is the rectangular one and this is also a rectangular column. Then say this is B by D and this is A, this is B. So the size of the column is A by B and size of the footing is B, capital B by capital D. Now let me just mark it differently, or you can differentiate this capital D, which is the total depth of the foundation, and here it is B by D is the size of the footing. Okay. Now what is this small d? This is the effective depth. Okay. So if we change this capital D just to differentiate it from the total depth, let it be capital L. Okay. Now what is this D? This is nothing but capital D minus clear cover minus pi by 2. Now Ks in this expression is equal to 0.5 plus beta C, where beta C is equal to B by A, and it should not be more than 1.0. Finally, the tau C, the expression for tau C is equal to 0.25 square root of FCK. So we can quantify the design value of the punching shear and design it accordingly. We'll see how to select bars and how to design it. We actually have to design it in such a way that it is less than this Ks into tau C. The controlling factor is obviously the size of the footing and the depth of the footing, right? So that we'll see as we progress. Now, in case of square footing, as you can see here, we have columns we have rebars in either directions. So let us mark it and I'll show you in a minute. So if you have This is the square footing. Then obviously we have to provide rebars to deal with the tension developed. So we have rebars going this way. And we also have rebars going the other way. Over the complete region. Now, for an isolated square footing, so this is a square footing. If you see the bars here in the cross section, so we'll have reinforcement here, and as you can see, the footing acts like a cantilever beam. So if you have a pressure here below this foundation, which is P0, how this cantilever is going to bend? It is going to bend like this way. So this surface will have tension while the opposite face will have compression. And that's the reason you can see we provide rebars at the bottom face, right? Now, these are the rebars in one direction, and then we'll have other rebars which are here in the orthogonal direction over the entire length, right? Now, why I bring this issue? Because for square isolated footing, these rebars, so this will continue in this direction. So these rebars are uniformly placed. So that point to be noted. So they are uniform. Now, when we have a rectangular footing, this arrangement is slightly changed. So if we have a rectangular footing, as you can see here, let me remove this column. So for this footing, we'll have one set of bars along this direction. So as you can see, this way. But there will be a special arrangement of bars in the shorter direction that I will come in a minute. Along the longer direction, we provide bars uniformly. So these bars are provided uniformly. While in the shorter direction, we have three different regions. So there is a central region and there is an outer region. Okay. So in the central region, we'll have these bars placed very closely, while in the outer domain, we have bars with a different spacing. And there is a specific guideline for this arrangement. So when we'll take the example of a rectangular footing, so we'll see we'll have central zone, and then this is edge zone. And as per Indian Standard Code, we have to distribute them accordingly, and we'll see how to distribute them when we'll have that example. So this more or less covers the basic steps of the design procedures that we are going to follow. But before we close, there are other points to be noted, and then we will take the example. Now, when we design a footing, we also have to provide a clear cover, and the minimum clear cover is 50 millimeter. Then there is a nominal requirement for reinforcement also. So the nominal requirement for concrete cross section with thickness more than 1 meter shall be 360 millimeter square per meter length in each direction. Recall, we designed this footing as a beam. So what we do, we consider a width of 1 meter, and then design the steel requirement for this 1 meter wide beam. So if the thickness of this foundation, if the thickness is more than 1 meter, then it should be 360 millimeters square per meter length in each direction. That is the minimum requirement. But the point to be noted, it does not supersede the requirement based on the effective depth, because the moment you set this thickness D, from there you can calculate effective depth, and from that you have a minimum requirement of steel for this beam design. So if that minimum requirement is more than this 360 millimeter square, then you have to provide that accordingly, right? So that actually covers the steps for foundation design. So now let us just consider an example. In this example, we have a wall supported by a footing. So we have a wall, and if I draw the cross section, so this is the arrangement. So we have to design this foundation. For that, let the thickness of this wall be small b. So the size of this footing is capital B. So we have B by 2 and B by 2. Then it is a wall and there is no monolithic action between the wall and the foundation. The wall is just sitting over the foundation, and therefore for this we already discussed that the critical section will be at the middle of the center line of the wall and the face of the wall, right? So this is the critical section. The distance between the center line, so this is the center line of the wall, is B by 4. Now for this design of this foundation, let us identify all the steps. Now for this soil, let Q naught be the shape bearing capacity of the soil. Then obviously the size will be B, that is the total weight divided by Q naught. Now on this side, just note on this side we consider 1 meter, right? So all these estimations are per meter run, because if you recall, we will design this as a beam with 1 meter width, and that's the reason the total load per meter run is divided by this Q naught. Now what is this total load? This is the weight of the wall. That means the total weight, this is W, and foundation also will have some weight, so W plus WF divided by Q0. Now obviously this will offer some pressure, uniform pressure, so we can quantify that will be uniformly acting below the foundation. So P0 is equal to WT by B, the B that we provide. Now what is the difference between this equation and this equation? The B provided here. From this first equation, it may come say 1.61. So we will provide 1.75. So normally the B provided is more than the B required from the shape bearing capacity, and that's why there is a difference between this one and the pressure developed. Okay. Now once we quantify the pressure developed, we have already identified the critical section. So bending moment M acting at that particular section is P0 times B minus B by 2 plus b by 4. So that is the distance square of this times half. So this is basically this distance. So what we do, we subtract small b from the capital B and divided by 2, that is the distance from the edge to the face of the wall, plus b by 4, that is the total length. So we get the total length and we know the UDL, which is P0, so we can quantify M. Now, there is another pressure acting, so which is in the reverse direction. So this W, if we draw the pressure developed at this surface, which is say P, so P is equal to W by B. So that will act in the reverse direction. So minus P times B by 4, that is the distance whole square by 1 by 2. So that is the net bending moment acting at this section. So what is the ultimate bending moment? It is nothing but 1.5 times M. Now, next step is to find out the effective depth. Recall the beam design, we have already done it. So D effective is equal to square root of mu by 1000, that is the width we have considered, times Ru. And we all know what is the expression of Ru. It is 0.36 FCK XU max divided by D, then within bracket 1 minus 0.416 times XU max divided by D. Recall, for a given material property, you can quantify this XU max by D, right? So if we know FCK, if we know XQ max by D for a particular grade, and then using this expression we can find out what is Ru, so we can quantify what is D effective. Then our next task is to find out AST, that is the steel requirement. Steel requirement is, again, we know from the previous design, that is 0.5 FCK divided by Fy within bracket 1 minus square root of 1 minus 4.6 mu divided by FCK B D square, right, times BD. Now, once we find out the steel, we also check the minimum requirement of steel. So there is a provision we already have gone through in beam design, so that we have to satisfy. Now, when we go for a footing, so we have the main bars going this way. We have already quantified AST, so we can quantify the size of the bar and the spacing very easily. So this is the main bar going this direction. But we also have to provide longitudinal bars in the orthogonal direction. So this is the longitudinal bars that we have to provide. Okay. So for this longitudinal bars, there is a specific requirement. Let us see. So longitudinal bars, they are at the rate of 0.15% for mild steel and 0.12% for HYST bars. So this is the minimum steel that we provide in the longitudinal directions. Then our design against bending is complete. We have to check for one-way shear. So one-way shear at a distance d from the face. So this is the wall and foundation arrangement. So this is the critical section at a distance d. So at a distance d, now we have evaluated d. So this is the critical section for one-way shear. And then in this case, because the wall runs over the entire length of foundation, there is no chance of having punching shear. So one-way shear is enough for this problem. For one-way shear, again, if you recall, our tau v should be less than k times tau c. This tau c comes from the material property, and this we have to see based on the thickness of the beam, that is d effective, and we can design this accordingly so that we don't need to provide any shear. Our idea is to keep this tau v well within this allowable limit, and then there will be no additional requirement for shear links. Only parameter we can adjust is d effective so that tau v comes well within this allowable limit. So that completes the design procedure. But before we conclude, just one point to be noted here. You can see the arrangement of longitudinal bars. Let us see, and then with that we will conclude our discussion today. So we have this longitudinal bars going beyond this critical section, right? So as you can see, this is the location of the critical section. So from this, we have provided this is the length of the bar. So what we have to check whether this length is sufficient enough. And for that, you all know the development length that we discussed earlier. So we have to provide sufficient length for anchorage. So this development length check is also required. From the dimension, we can quantify this length. We have to check the LD. You all know the expression for LD. We will see when we'll take an example with some numbers. So this length should be more than the LD. If by chance this is not, then we can actually turn it and take it other side. Or otherwise we can extend it and we can go this way also. In any case, we have to provide sufficient length of these bars covering the minimum requirement for this development length. That point to be noted, and with that only our design will be complete. So we have to check against bending, we have to check against shear, and then finally against the development length. And that completes the entire design procedures in steps. So we'll see when we'll put some numbers how to design exactly the steel and how to detail it in our next example. But before that, what I want you all to go through this note and just make sure that these design steps are clear to you, and then we can easily put some numbers and we can see how we can design foundation below a wall. That will be there in our next lecture. Thank you very much.